Good day, my name is Norm Kirchner and welcome to the LabVIEW 2014 Developer Education Day. I wanted to talk to everybody today about principles to code by, designing and defining for beyond today. This is going to be a presentation which is a call to action for everybody from beginning LabVIEW programmers all the way up to architects and center of excellence individuals in large organizations. We each need to reevaluate and establish our own principles that we need to actually code by to ensure that the code that the next person uses down the road, be that you yourself a year from now or the person sitting next to you a week from now, will appreciate the fact that they were adhered to, thought of, and actually developed to. First off, I need to have a call to panic, not even a call to action. We need to recognize some issues that are going on in industry that we need to improve. First off, we can't just say that when a program runs, it's complete. Too often do we get to a point where all we are doing is scrambling to get things done, get our program running, and the minute that it gives us a result that seems reasonable, we stop development on it. Just because it runs does not mean that it's done. We need to stop creeping down the quality bar. Often because of time, we don't have enough ability to actually do things to a level of quality that we might be desiring deep down inside. And so what do? We slowly creep down what's acceptable in our organizations or even for ourselves. And we need to stop doing that. Also, we need to start coding with vision, because coding without vision is like Crayola in the dark. I have asked some people about if this diagram was a good example of some VI block diagrams that they may have seen to illustrate this point. And the reality is that they said this is almost cleaner than some block diagrams that they've seen developed. Specifically without any vision. It was just a scramble to get it done as fast as possible. There's a question I'd like to ask the audience. I'd like everybody to ask the audience, even the people presenting this, is what level of developer are you? We need to know how many people out there are just in the audiences, specifically for the purpose of this presentation, who's just a basic ExpressVI user just trying to get a sine wave and see what happens. Who's using sample projects, they're a little bit more advanced, they're trying to create more complex programs. Who's created a complex program so advanced and so complex that it turns into a rat's nest of wires. And lastly, who actually stops, or doesn't stop, but starts programming not from a block diagram, but from a functional design, something like UML, to actually ensure that what they're trying to do is going to code up before they even get going. The relevance behind asking these questions is because each one of the individual principles that we'll be talking about today have different level examples that we can stress. Whether you're a beginning LabVIEW programmer or a novice, whether you're an intermediate to advanced programmer, or whether you're an architect all the way up to a LabVIEW champion, really. We can go different levels. Each one has different complexity associated with it, but the principles remain the same. So now we have our call to action. We need to start forward engineering and stop reverse engineering. All too often we're like this guy in the graphic down here who's trying to figure out which cable needs to be changed from one port to the next, because the guy or the girl who set this system up before him didn't think about his poor soul and how late he's going to need to stay up just to try to resolve whatever problem there is. So why did this happen? Why does this happen within our programs? Well, the problem is that code rarely dies. We'll create a proof of concept, or you'll create some demo code, or somebody will ask you to put something together to make sure, hey, this can be added into the system. But what happens to that code? It rarely dies. Somebody takes an example that you gave them, wraps it up, and makes it the cornerstone of their whole application, and you never even thought of that. And next thing you know, they're calling you 2 years from now wondering why their program is crashing, because every time it calls your function, which actually wasn't a function, it was an example which you expected to die right away. But instead now it's roaming around the reuse libraries in terms of your organization. And the only way to kill it is to tear out all the wires and start from scratch. Also, Project scope is never static. How often have we ran into a scenario where we start designing something and the scope doesn't change at all? It's exactly the same at the end as what we predicted at the beginning. That is, I cannot think of an individual scenario where that has been the case for me over my years of programming. And so it shouldn't become a shock to you that your program and your project is going to change over time, well after you have started coding and well after probably the completion of your actual program itself, or the project. Also, progress means forward motion. Very specifically, if we are reverse engineering code, if we have to open up somebody's block diagram to figure out what's happening, and we are wasting a lot of time just trying to decompile in our brains what is going on, we are moving backwards and then we will go forward, and that will mean that we are going in circles. Other people have caused you to go in circles, you are causing other people, or even yourself to go in circles every time that you just can't walk into a code and start doing what you know you need to do. So what do we do about this? Well, I like to use a building as an illustration of what our programs need. Buildings are flexible. If we look at this, this is a picture of Taipei 101. This is a building that actually moves, much like every skyscraper out there. And in order to illustrate that, I wanted to show a video of this mass damper system that's one of a few in the base of Taipei 101 actually moving. And so what you'll see here is this mass, the 750-ton weight, is moving just a little bit. And in a brief moment, you'll notice the byproduct of an earthquake that happened back in 2008. You'll see the extreme movement of this. And the crowd actually even reacts to how much it's moving while this earthquake is going on. The top of the building is moving as well. In order to illustrate that, during, I believe, that same earthquake, you can see this building right here slowly swaying. Now, if this building had been rigid and not swayed, had not flexed due to the earthquake, this building would have collapsed. And very often when we actually step into a system of software, or we create a system of software that has constants all over the block diagram, has static paths all over the block diagram, systems that presume that I'm only ever going to have 4 inputs to my to the entire acquisition process. The minute that something changes, the code breaks. And you have to spend a significant amount of time dealing with rebuilding code bases just to handle that little bit of change, as opposed to building flexibility in from the beginning. So how can we actually accomplish this? Well, I'd like to give everybody in the audience, everyone listening, and anybody that'll remember this acronym. SMORES. Scalable, modular, reusable, extensible, and simple. These are principles that I have lived and breathed for over the past 10 years, so that every piece of code that I go back to over the past 10 years, I can actually be proud of. And I don't look at code that I've created a long time ago and cringe. And even though I've learned more techniques and I've become a more advanced developer over time, the techniques and the principles I adhere to have remained constant. A quick shout out to the originator of this acronym, Tim Jones. Used to be my mentor a long time ago and the originator of SMORES. And so every VI, every program, every architecture that you put together, you need to ask yourself this core question. Can I make this? And then you start down the acronym. First off, how do I make what I'm doing scalable? How can I take what I've created and go n+1? I've got 5 channels. How can I make it 6 channels? I've got 5 files I need to read on disk. How do I make it 7 files I need to read on disk? I have 8 RF analyzers. How do I make it 50 RF analyzers? Now, this might seem like an extreme example. The reality is we always end up with some change, and often it's the exact same thing, just doing it one more. And so we have to ask ourselves, what happens on the block diagram? How unreadable would this code be in order to add these new functions? Would I need to add 5 new wires to the block diagram? Would I need to add 50 new wires to the block diagram? If you need to add that many, think about what it's going to look like. And if you think that would look ugly, then you probably need to take a step back and say, this needs to be done in a different manner. You need to ask yourself, how much time is it going to take to integrate and refactor the code to add this in? Do you have to make space on the block diagram? Do you need to add more memory to your system? Do you need to do you actually even need to change the program at all? Should you have to change the program at all? These are simple questions that we need to ask ourselves because we know very often we'll need to do the exact same thing, but one more. Also, ask yourself about the user experience. If we're talking about a front panel, if you have a cluster that defines your DAC channel and you have 3 of them and therefore you have 3 clusters on your front panel, what's going to happen when you have to add another 3 more? Is the user going to have to start scrolling around your front panel to find the relevant information? If so, that's a bad user experience. Let me give you an example of that. Underneath the scalable section of the project, you'll see an example for the BF enum. Now this is an enumeration that was linked to commands associated with the device under test. Now originally there was maybe only 15 commands, so they used an enumeration and they said if somebody wants to execute a command, they'll select the enumeration, hit execute, and they're off to the races. But unfortunately, that list of commands grew and grew and grew. Not only is it unusable on the front panel, but also on the block diagram. How do you get to what you need to get to easily? How do you change what you need to change? It is not easy. We needed a more scalable solution. How about if it was something like this, where you could just simply start typing and then you get the list of commands that you wanted to actually execute. I don't know, I ask everybody that's listening, watching, and that you'll be presenting to as well, what does this look like? And hopefully the answer will end up being QuickDrop. Well, that's right. That ends up being an extremely scalable solution for a vast number of individual commands that you need to get to. You want to be able to easily search the list and get to what you need and then allow that to be executed. Now the block diagram for this is inherently more complex than the other one. And so in some cases it may or may not be warranted, but we're going to get to simplicity later. First we want to ask, how can we actually make something like this scalable? I'd like to use another example of what we saw on the slide deck right there for actually doing transformation of a G-object. This is something that we would commonly do to actually do a detection of, hey, is this specific object coming in of this type? If not, is it of this type? If not, is it of this type? And this is we are continuously casting over and over again to determine what is actually accessible. What happens when I need to add 50 more things to this actual list? It becomes unreadable, it becomes unusable. So I ran into a scenario very similar to that. And so I ended up deciding to say, I'm going to make something that actually is scalable. So what are some of the scalable structures that are in LabVIEW that you can add 50 things to potentially? Well, as we saw, there's the enumeration, and so it kind of gets out of hand once it gets past 50. But for this individual application, when we need to test a certain number of things that we can cast to, how about a case structure that we can very easily move through that condensed list of actual things? And so this is actually based on the Manycast design pattern that's available online. Everybody can search for it, and all these VIs should be accessible online at the time of viewing all of this. But this is a design pattern that you can use in your program when you want to go from something that looks like this to something that just very simply looks like a stack sequence structure where you can get to what you need. Lastly, a great example is also this idea of a number pad. This is something that I created a long time ago. But I started off thinking about, well, this number pad is likely not going to stay a number pad. Chances are somebody, a manager, or me is going to say, you know what, I want something more. I probably want to have a fully fledged keyboard. But imagine if I would have started out coding it up like this. where every individual key, 3, 4, 5, 6, 7, had its own actual event case in the event structure itself. Imagine what it would have looked like with that many buttons. It would have been very difficult and cumbersome to actually code all of those up. Well, how about if I took a slightly different tack, and in the legacy numpad, instead of doing that, I very simply used a little bit of dynamic registration for mouse down, and that's it. I'm handling the key down in case somebody's keying on the keyboard, but every time I press a button, I run this code, and it takes the text from the button and adds it onto the actual string. So now, if I wanted to do something like e to the negative 3, no wiring. I added a new button. This is completely scalable. I could add 1, I could add 100 buttons. It doesn't matter. The program will operate in the same fashion without me needing to do anything. I went n plus 1. Same thing, just doing it again and making that as easy as possible for me or the next person down the road. Next, you need to ask yourself, or once again, this is a call to everybody, all of this acronym, all these principles are things not only for you to start to ask yourself, but to stress to your organization, people that you work with and code that you look at, ask yourself as you review it, how can I make these things, or how did the person developing it think about making these things in this fashion? In this case, we're talking about modularity. I like to use the word functional containment. Functional containment helps prevent Plato syndrome. Plato syndrome is what happens when this is what the Plato Corporation would actually have us believe our children would actually create. They would create this monster in the background that has blue and red and white, and if they wanted to make this monster up front, well, heck, they would just pull off the lips and pull off the blue, and there'd be no problem. You wouldn't need to run to the store again to actually buy more Play-Doh to create a new monster. But what ends up happening? This is what ends up getting created. Now, although the little girl in the background is extremely happy about her monster creation, what about when she wants to make something with orange again, or yellow, or the magenta? How likely is that going to be? It's not. We do this exact same thing when we don't take and hold on to principles of modularity when we create our code. When we don't ask ourselves, what are the bounds of certain functionality that I need to keep together and separate from the rest of it? When you go ahead and you take display formatting nodes, property nodes about the color of a graph, and you put it right next to the algorithm that creates a piece of data, or you're putting event structures that handle mouse over, and you merge them with event structures handling things associated with external user events that are coming into the program. You have merged different functions of your program into one section and completely destroyed your ability to have reusability, to severely impacted negatively your ability to debug code, and it's a whole other list of things that go wrong when you don't put good functional bounds on your program. You can think of this as, what are logical boundaries? If I had to put a chunk of code into a sub-VI, could I even do it? If I had to put a flat sequence structure around a section of code, would it actually be its own module? Could you call this piece of code a section? Does a given structure, do the things inside of a given structure do too many things, when really it should be two different structures, each dependent on their own set of functionality? You need to ask yourself, when you start making things modular, also, how will this module that I've created, how will it fit into other code? This comes along the lines of creating an API. And then also you have to start asking yourself, how easy is this module that I've just created to deal with? I wanted to give everybody an idea of what a good definition of modularity is by simply saying, I have a front panel, and on that front panel I want to take the description of each one of these buttons, and as I mouse over and mouse leave, I want to display this and then have that description go away. So you'll see that as I mouse over these, I end up getting the description displayed in this over here. The way that I accomplish that is the way as many LiveView programmers would. I have an event structure. I'm just going to use that exact same event structure and put that functionality as another case within it. When I mouse over, I'm going to get the description from that Boolean, and then I'm going to go ahead and put it into the string. And when I leave the mouse, or the mouse leaves the context of the button, I'm going to change that string back. There's more going on inside this event structure, but for the sake of whatever's going on, we just shrunk it down for visual purposes. But what if I wanted to create functional bounds on that? What if I wanted to use it in another program? How would I do that? I would have to recreate those very same two cases in my event structure, and I would have to register each one of those buttons for that exact same behavior. Well, that's not good enough. That's not modular. That's Plato. So I have the exact same program that doesn't do that functionality right now. But I want to go ahead and make that possible. So what I'm going to do, take that block diagram, take this tool, it's a brat VI, it's a child VI that controls the parent, and I'm going to run that very same VI. And indeed, ain't that slick. So what did I do? I took that very same functionality that was very easy just by adding two cases into an event structure that already existed, and I turned it into its own module. This VI in particular has a settings panel. If I wanted to add that functionality into that panel, and say within that settings panel I wanted that same functionality, it's a little bit overkill at the moment, but let's put a description in there. I could take that very same function, add it to this block diagram, run the VI, and you'll see that I have that same functionality in another sub-VI without really having done anything. So once again, I took a concept, an idea that was merged together with a bunch of other things, I put logical boundaries on it, and now I actually have made it reusable as well. So one thing about reusability is we need to make sure that we think about it as we're developing stuff. Don't develop something and then at the end of it call it reusable, because in the reality it might actually end up being refuse. You don't want to take code that wasn't created with the intent of making it reusable and call it reusable. We actually want real reusability. Now, does reusability always have to mean that you're taking code that you've used and just dropping it into your next program? The answer is absolutely not. Very often we have to create things with reusability in mind, and the only thing that we can reuse is the design of which. But that means that we don't have to think about all the things that would make this section reusable again. It's just a re-implementation of something that we've already done before. We know where the kinks are, we know where the rough edges are, and we can actually reuse that concept in other VIs. The idea of a brat VI is the exact example of that. Every brat VI actually ends up being unique, but the basic design of it, where you go to the parent VI, you get the references, and you register for an event panel, that is a reusable design. So we have to ask ourselves, as we're developing something, to figure out how reusable is it, we have to say, is this one of a kind, one of a few, or one of most? Beyond that, we have to realize that big or small, reuse is time saved. That means that when we're actually looking at something, when we're developing a part of our code that is now scalable, functionally contained, now we want to say, how reusable does this need to be? Well, even if it's a small function, you can recognize that, you know what, I could probably reuse this again in the future. Somebody might reuse it again in the future. So I'm going to design it like it might be reused in the future because it will be time saved in the future. Because we are thinking beyond your immediate use. Now, think about this. If you created a bunch of sub-VIs for reusability, but you left the default values exactly for what you needed, so you didn't have to wire anything on the block diagram, how easy would that be for somebody else to use? Now, your block diagram might not have constants over it for your specific application, but maybe a 30 millisecond timeout doesn't make sense in the next person. Maybe a 5-second timeout is way too long in somebody else's application. But you have to ask yourself, if this function, whatever I'm doing right now, might actually get used again, what will be the things needed by default in terms of inputs to the function? There's an example of a viewer where I wanted to be able to run a VI and then very quickly look at sub-VIs that are selected inside of a project view, and then just scroll through their block diagrams. And I realized upon developing this little application that just kind of loads the block diagrams inside of a little window that this is likely useful beyond my immediate needs. So I designed it that certain pieces of the functionality could very easily be replaced. The design of the block diagram, the actions that were available. This doesn't have an API, so there weren't necessarily any default values, but it was the behavior that I wanted to make sure was reusable. And indeed, I was able to take that very same design and apply it. My apologies, Quick View is actually the one to open up first, which has that ability to view a variety of individual things by clicking the load button. And then Class View is actually the one that will actually load up an entire class. And I'm actually going to go ahead and use the extensible class where I can actually drag and drop this into here. And now, instead of looking through what's selected in the project, I'm actually looking through VIs associated with a given class. Once again, this program was created, all I needed to do was look at a bunch of block diagrams. But instead I realized there are certain things that I'm going to want to do, loading and unloading, viewing the individual icons of whatever's selected, things beyond my immediate use case that made it useful. Now when it comes down to reusability, depending on if you're not an advanced developer, you might not be able to create reusable components. You might not be at that stage. That's fine. Use tools that are already out there that are available. You need to do FTP? There's a tool. You want to go to XML? There's a tool. You want to be able to do things with arrays. You want to do things with trees. All of these things and more have reusable components already available for you. If you're not going to create your own thing, use what somebody else has already created for you. If you're at an organization and you're one of those immediate developers, go ahead and start thinking of templates. Start thinking of how can you actually create things for your organization that might fit within here, templates that are already created. Or if you're not going to create your own, use templates that are already there. A lot of those things in the package manager are just tools to drop and use in your program. These are actually new starting points for specific things. If you are maybe more of an advanced programmer and you are working in an organization where you're going to create a system of software and not just a program, use frameworks. There are some built into LabVIEW. Active Framework is one of them. Or there are things out there on the web. There are two that come to mind. One is called JAMA, I believe from a company called Jet Engineering. And also there is Aloha. Aloha is another one that's available. Both of these are available on the web. If you or the people watching this or the people that you'll present to have available, or maybe you're even thinking about creating your own. But the reality is that as you move up the skill level, you start thinking about better and better starting points. Now, each one of these better and better starting points requires you to adhere to the principles of those new starting points. If you're starting from a framework, you need to actually use the framework in an appropriate fashion. If you're going to start from a template, use the template as it was designed to. Because if you don't do these things, you'll end up potentially, if you're not ready to, end up in a very precarious scenario where you've designed your system off of one of these things. You've exploited a loophole that you found, and next thing you know, your program ends up being very unstable. So part of the reality of starting from a better starting point is respecting the tools and the functions and the time that somebody else put into it and where the bounds are on what they've created. So there's a little give and take with reusability, but it's always better than starting from a block diagram. Practically anything's better than starting from a block diagram, unless you just want a VI that doesn't have a broken run arrow. Extensible. This one is actually something I hope everybody that talks about this can speak to. The original acronym did not have extensible as part of the acronym. It was actually a little e, just like the O that's been optimized out. The E was added when I recognized that extensibility was a key principle to follow, and the acronym itself had room for growth. And I extended the acronym with extensibility as the E. And that was extensibility by luck. But as we start to develop our programs and help other people develop theirs, we need to ask ourselves, ask them, how can I make what I'm doing extensible? How can I allow the person who's going to use this in the future and develop off of it in the future, how can I make their lives easier? How can I make points that I know they're going to want to change, hot spots of growth? How can I make that easy for them to implement? What are some of the ways that we can actually do this? Now, before I actually get into this, and just in case extensibility really is not a term that most people have definitions for in their head, I wanted to raise, as an example, an iPhone or a smartphone. These are some of the most extensible devices on the planet. I can say that with a lot of certainty because when you get a smartphone, it really doesn't do that much, does it? It maybe has a messaging application, it definitely has a telephone, maybe has a calendar, and that's about it. And every time that you download an application, you are extending the functionality of this phone. How can we do this? Because the people that design the software and that design the hardware recognized that people are going to be using these things, the functionality of this, in ways unpredicted. As we develop our programs, we don't need to create an Android operating system. We don't actually need to go to the extent of this, but we do need to be asking ourselves, how might somebody want to add functionality to this program? And if you're talking about, I'm just a simple developer and I don't want to do any kind of fancy coding, that's fine. Make a home in your code for what might need to be there. Go ahead and just take, I'll use an example. I'm just going to open up the watch. Now this code isn't going to do too much, but it's a good example. If I know that somebody's going to want to do some specific code, just in case something was created new, but I don't want them to put their code inside of where my code is, by all means, wire something up. Let them decide if they want to put something here before they enter into your code. Because if you don't give them a home to put their code, if you don't give them some directive as to how something should be added into a piece of code that you've already created, they're going to put it in places that they shouldn't be putting code. And that's just a sad reality. And so if you give them a section of code that says, put your init code here, guess where they're going to put their initialization code? Well, they may put it somewhere else, but at least there's a higher likelihood that they're going to put their code in the home that you've declared it for. Now this is about extensibility on its most simple form. Another way of having extensibility is you can actually go ahead and just turn something like that into a sub-VI. Now, although in the block diagram of this sub-VI, nothing really is going on. It just passes through the values, and that's about it. But it's not hurting anything. And now, if you don't want somebody to say this is your application, and you don't want somebody getting to your block diagram, well, guess what? The only thing that they need to modify, they just need to modify the VI that you've given them. So these are two very simple ways of thinking in terms of extensibility. Where is your code going to need to be modified in the future? And how hard is it going to be for that person to add that functionality? Now, one of the great things about LabVIEWs within the past, oh my gosh, since what, 2008 or before, we've had classes in LabVIEW. And the ability to actually extend the definition of a given program has been extremely powerful. I'm going to open up a very simple demo. It's just a little bit of a timer code that has kind of a start, stop, check time, and then end. There's a lot of other code in here that we don't need to pay attention to. It's a good demo, but for the purpose of extensibility, we don't need to get into it. But I know that I have a timer. And I have a class that is my timer session. And I know that here, inside of this VI, I take that timer and then I run an initialization function that's locked down. It's a framework piece of code. But in the guts of that code, somewhere in there, I'm actually calling that function deep, deep, deep down in here. And it's based off of the specific class that's wired in. Well, let's actually go ahead and take this idea, and this VI that gets run on the very first acquisition is going to do some things. And I can have it actually go ahead and announce what it's initializing the data on. So when I run this VI right here, it's just going to do a basic countdown, but it's telling us we're initializing data on foo1. And then I'll do a basic countdown from there. Nothing too exciting. Well, how about if I actually go ahead and say, you know what, I'm going to create a new class. Leave it as class 1. I'm going to extend the actual original inheritance of this class to say I'm going to be a child of my timer session. And then I'm going to go ahead and change, or actually extend, what happens when I initialize my session data. Now it's going to call that parent function, but now I'm going to have it call another chunk of code as well. Actually, what I'm going to do is go inside of here, kind of take that, drop it out here for the sake of time. And I'm going to go ahead and I need a format specifier in there, leave that %s. And then very simply, I'm actually going to allow myself to change this into something that I actually wire in. So I'm going to turn this into a control, wire it into, let's say, the top here. And now in my diagram, I'm actually going to go ahead and take that new class and wire that into the top. Run the VI, the original announcement of that I'm initializing a session, and then my new code. Without changing anything really underneath the hood, I created a class, then I sent that class into the framework that's already there. I've extended the functionality, very, very easily. In this scenario, I said, I'm going to create an API. And I know that very likely somebody's going to want to do something unique at the start and also something very unique at the end for the very first obtain and the very last release. And so I put that into the code. Initially, I didn't necessarily take advantage of it, but I knew that somebody down the road is going to want to do this, so I gave them a home to put code associated with specific actions. Just as an iPhone gives developers, app developers, the ability to respond to specific inputs when things happen in the system, like when you rotate the display or when maybe a call comes in and it leaves the program. We have to ask ourselves those same things. Where are things likely going to change, and how can we make that as easily as possible? And so finally we get to the last S, the second S. The S that always belongs at the end and never belongs at the beginning. We must ask ourselves, how can we make this simple? First, we must get creative. We have to ask ourselves, how can we make it scalable, modular, reusable, extensible, the entire acronym, or all the way up to extensible. And then once we get to that point, once we have figured out what we need to do or what we can do, then we figure out what we really need to do. Because all too often, we start off and we ask ourselves, first, how can I make this simple? And unfortunately, you end up with a different S at the end. It's so important to think about this acronym, these guiding principles of s'mores, and recognize how we're adding complexity each step along the way. We're adding complexity so that this building can flex and not crumble down. But when we finally get done to the end of the design, that's why it's designing and defining for Beyond Today. Because we haven't actually developed anything. We've only asked ourselves a bunch of questions. And then after those questions have been asked, then we go back and ask, how can we make it simple? How complex does it really, really need to be? Because you might say, I want to make the most scalable, modular, reusable, and extensible program out there. And you know what they're going to do? They're going to create a VI connector pane with 32 inputs, and they're all going to be variants. There, you've made the most scalable, modular, reusable, and extensible VI in existence. But it's unusable because it's too complex and not simple enough. So we have to ask ourselves, if I had to describe what I'm doing to somebody else, and it's too complex, is that complexity warranted? Can you justify all these things that you're about to put in there? Another thing, simplicity goes awry when you do s'more and you create s'more in your program and you don't actually, and you use that as a substitute for good requirement gathering. If you are told, create a program that monitors temperature, what are you going to do? Well, I'm going to create a program that might be scalable, modular, reusable, and extensible that can read up to 10,000 channels of temperature. But who are you talking to? Are you working with a customer that will only ever facilitate 5 temperature sensors? Ever. Maybe it'll go up, but it's never going to be more than 15. Do you truly need to create a program that can handle 10,000 temperature sensors? You have to ask yourself, you have to ask the people that you work with, you have to ask your customers the necessary questions to determine how complex something may get in that future. How strong will that earthquake be when the winds come blowing and the grounds are shaken? So now we get to the fun part. So what? So we've learned all these things. We've asked ourselves these questions. What do we do with it? Well, this is LabVIEW Developer Day. This isn't just LabVIEW Doer Day. We need to develop not only our code, but also ourselves. We need to develop ourselves as mentors. If you have wisdom, you must share it. And in order to have wisdom, you have to share it. This, I believe, to be paramount in your own growth as LabVIEW developers and then helping your organization around you. Because if you just think that you're coming up with, if you've been given some creative ideas and you don't share it, chances are you will be becoming self-reliant on your own standards of quality, and that quality bar will never move. And also the quality bar of the people around you won't move either. It's a two-way street that you need to be part of. So is change good or bad? Change is inevitable. We can't get away from it. Every time that we work on a program, things are going to change. So stop thinking about the programs like they're going to be static, like they're not going to change. And even though it's scary, we need to face it. So what do we do to change it? We need to improve our processes. Now, the processes that we have are not about, we're not talking processing algorithms. We're talking about the process of which we develop code, the process of which we guide people to create code, all these things. And we want to improve it. But we can't improve it if every time a bug comes up, we're smacking it down like playing whack-a-mole. We have to start tracking how things are changing. We have to start tracking how much time things take to fix. What kind of things are breaking? Identify them, quantify them. Now, this takes time. And right now, the time you need to just do your job is probably greater than the time you have available. And so your manager is asking, why should I give you any more time? Because really, the time needed now and the time for change is way more than probably what you have available. Well, there's an answer to that. It's not about how much more you're going to make. It's about how much less you're going to lose. Because you are burning money. You're burning stacks of money. Every time that you have to go into somebody else's code and unknot all of the wires, all of the diagrams, all of the structures, just to try to figure out what's wrong, only to realize that somebody's using local variables all over the place and you didn't catch one of them. Or somebody created a program that could only handle four files existing in one directory at a time. Or they never thought about that this program was going to be put into an executable, so they didn't take into consideration some of those things, some of those caveats behind doing that. And so you waste time, you burn money, you spend time trying to teach people things that they may have learned by themselves if they were guiding principles were only conveyed and people were held to a certain standard. And so we need to start doing things that we can measure and we can improve. And so the first steps upon leaving is we need to start setting a higher bar for all that we do and see. We need to start saying we expect more quality. Lower your threshold for pain. Stop looking at diagrams that you know are not done well. Say that they need to be done well before you continue to try to debug, and guide those people, or even yourself. When you start to debug something, stop just trying to solve the problem. Get the car running again. Finish the car. Finish the problem and actually make it clean code and then move forward. And we need to start tracking the cost of change, finding out how much time it takes to fix bug. How much time is it spent reviewing somebody else's code? Because if it only takes you 20 minutes to review somebody's code, but it used to take you 2 days to review somebody's code, you know things are getting better, especially if you are grading the quality of code on the same set of standards. Things like coding standards, coding guidelines, things that you need to have inside your own organization, or just guiding principles. A standard set of 5 questions, like, is this scalable? Is this modular? Is this reusable? Is it extensible? And is it simple enough? And if you don't like that acronym, that's fine. If you don't like those principles, that's fine. Come up with your own. Stick to them. Raise them up. And don't just raise yourself up in the middle of your organization. You need to be worried about raising all the people around you up. Mentor them. Create tools for you and your organization to use. And then be the center of excellence. Because once these people around you have been raised up, you'll go that much further. As a close, I'd like to say that this is something that I would recommend everybody writes down in a notepad, in a binder. However, create your specific live-by codes, the things that you live and breathe when you create your programs, when you create your architectures, when you make your systems. And I'd like to give a quick note out to the contributors: Brian Powell, Brian Kindiger, Tim Jones, Nancy Hallenbeck, and Eli Carey. And for things, ideas, feedback, I would recommend that you go to lavag.org. This is a website which is not run by National Instruments. It is completely independent, full of people willing and ready to help and eager to help you be the center of excellence at your organization. And if you're looking for more, I'd recommend that you actually look towards becoming CLD or CLA and then attending the corresponding summits for those. You will find a wealth of information in a community of people eager to share their ideas and help mentor and teach you how to mentor as well. Thank you very much.